Hi, let's talk about a problem in linear regression. The title of this video is going to be Multiple Hypothesis Testing and a Bonferroni Correction. Just to give you a bit of a preview of what you're about to see, well, we're going to have some null hypothesis that's in some sense a combination of two or more different hypotheses, and we're going to employ a strategy that requires some sort of correction so that our tests end up with the right level. The model that we'll be working with is a linear regression model, y equals x beta plus epsilon, which I've also written here, just to give you an idea of what the matrices ought to look like. X is our design matrix, that's n by p. We're going to assume it's deterministic. So there's one row for each of the observations. So there's a corresponding y and a corresponding row x. And each row is going to be p-dimensional, one for each of the covariates. The parameter beta is going to be a p-dimensional vector. It's unknown. Epsilon is we're going to assume is a Gaussian that's n-dimensional, has mean 0, and covariance matrix sigma squared I. So this tells us that we're in the homoscedastic case, so that the components of epsilon, which are epsilon 1 through epsilon n, are IID Gaussian with mean 0 and variance sigma squared. The null hypothesis is going to be 0 less than equal to beta 1 less than equal to beta 2. The alternative hypothesis is going to be its complement, so not the negation of whatever it says for the null hypothesis. We're going to ultimately want to design a test against this null hypothesis at level alpha equals, let's say, 5%. Okay, so in what sense is this a multiple hypothesis testing scenario? One way to look at this is to read this as the following statement. So this tells us something interesting about our unknown parameter beta. It tells us that beta 1, the first component of our parameter vector, is non-negative, and that beta 2, the second component, is at least as large as the first component. The operative word I used there was the word and. So another way to write this is 0 less than or equal to beta 1 and beta 1 less than or equal to beta 2. These two are equivalent. So what is H1? What is the alternative hypothesis? Well, since it's a negation of this, one way this can be false is when this is false, or when this is another way is when this is false, or possibly both. So the negation of this is equivalent to 0 greater than beta 1, or beta 1 greater than beta 2. And this or encapsulates the possibility that both could be false both of these could be false at the same time. The strategy we'll be using is as follows. We know how to test against this null hypothesis on its own, and we know how to test against this null hypothesis on its own. So why not design tests for these two statements by themselves, set them at some appropriate level, and combine them together? And our final test is going to reject when it tells us to reject for one of these, or possibly both. Okay, so for the sake of argument, let's call H0 with the superscript 1, this first half, 0 less than or equal to beta 1, H0 with the subscript 2 with beta 1 less than or equal to beta 2. These are not actually our null hypotheses. Our final null hypothesis is this one, but for the sake of argument, I'm going to write these down separately. And let's associate with these tests psi1 and psi2 at some level alpha 1 and alpha 2, with the aim that our final test is going to look like psi defined as psi alpha 1 at level alpha, or psi of 2 of alpha 2. And this word or, I've taken advantage of the fact that, well, the way we're going to encode these by standard notation is this is going to output 1 when it tells us to reject, and it outputs 0 when it tells us fail to reject. So this word or tells us that we should reject when this outputs 1, or this outputs 1, or both of these output 1. And another way to write this, just to drive the point home, is this is the maximum of the two tests put together. Okay, so now the question is, what level should we test this null hypothesis at, and what level should we test this null hypothesis at, to be able to end up with a test using this strategy of 5%? Well, one thing we can try to do is, well, why not just set alpha 1 and alpha 2 both equal to alpha? Does that work? Well, let's see what happens. For the sake of argument, let's say that this test has level exactly alpha 1, or has the probability of rejecting H0 under H0 equal to alpha 1, and the same for this. So this outputs reject with probability alpha 2 under H0. Okay, so the probability that psi our composite test outputs reject is going to be equal to the probability that psi 1 says reject, or psi 2 says reject. Really, these should be 1s, but just to make this more readable, I've written it this way. And this is at least one of these events on their own. And we could have said the same thing about same thing about the second event if we replaced this with a 2. Okay, so now we sort of understand why this is not the right thing to do. Well, because we assumed that in this test alpha 1, we naively set it to 5%, this is going to be equal to 5% under our worst case assumptions. So we no longer have the guarantee that this test has level 5%, because it's greater than equal to 5%, not less than or equal to. Could be the case that we have 5.1%, if it's the case that this union of these two events has probability slightly larger than 5%. So clearly, setting both of these levels equal to 5% is not the right thing to do. So this is where we require some sort of correction, which we'll call the Bonferroni correction. Okay, and it relies on the following idea. It should be a review of a concept you've seen in probability theory called the union bound. And it's the following idea. If A1 and A2 are events, then the probability of A1 union A2 is at most the probability of A1 plus probability of A2. So here, A1, we should think of as the event that the first test says reject. And A2 as the probability that the second test says reject. So what does this tell us? Well, if we set the levels of these two tests at, let's say, 2.5%, we end up with the right guarantee. In other words, if we set this to be at most 2.5%, then in total, this is less than or equal to the sum of these two, which is 5%, which is the right kind of guarantee we want so that we can say that our test has 5% level. Okay, in general, if we have multiple hypothesis testing where we have, let's say, k different hypotheses, AK, and these are the events where our tests individually, say, reject the ith hypothesis, well, we're going to want the kind of guarantee that says A1 union A2 union AK is at most some level alpha, and it suffices to say that because this is bounded by the sum of the probability of each of the events individually, I equals 1 to k, well, it suffices to set each of these at most alpha over k. In the end, we can bound this by alpha. So this is what is known as the Bonferroni correction. It's a simple application of the union bound where if we have two different hypotheses, or more general k hypotheses, we can set each of the levels individually to alpha over k. So this is in some sense an overcompensation because this inequality is in most cases not tight. So this equality is not achieved unless A1 and A2 are mutually exclusive. So in a lot of cases, this is an undercompensation, but this works in general. So that's why it's widely used in statistics. Okay, so now that we have the levels in mind, let's think about, while I erase and move on to the next part, what these tests ought to look like.